Hey everyone, and welcome to The Explainer. Today, we're zeroing in on something that honestly might sound just a little bit dry on the surface, but it's actually the unsung hero of modern AI production stacks. It's a concept that is entirely load-bearing for the systems you and I interact with every single day. We're talking about Natural Language Inference, or NLI. It acts as the ultimate duct tape holding text understanding together. Okay, let's jump straight into this terrifying reality. Picture this. You're a developer. You just built this highly sophisticated summarizer, or maybe an answering chatbot. It reads a document, processes it, and outputs a perfectly confident answer. Let's say it just says yes. But here is the absolute nightmare scenario. How do you mathematically, systemically know it didn't just completely hallucinate that answer? I mean, how do you prove the text it generated is actually supported by the source document?
Well, the answer to that developer's nightmare is natural language inference. You see, the massive engineering headaches of hallucination checks, grounded question answering, and even zero-shot classification, they all basically reduce down to this one incredibly powerful task.
So here's our roadmap for today. We'll start with the AI trust problem, then meet NLI, break down the three labels, look at datasets and architecture, reveal the 2026 stack, and finally cover the pitfalls to avoid.
All right, let's dive right into Section 1, the AI trust problem and solving hallucinations.
Now, what's really fascinating here is how three seemingly totally distinct problems are actually grouped together. First up, summarization hallucinations. That's where your source document says one thing, but your summary claim just invents a totally new fact. Second, ungrounded QA fabrications. This happens when a retrieved passage doesn't actually support the generated answer at all. And third, zero-shot classification. Imagine needing to categorize 10,000 news articles by topic, but you have absolutely zero training labels to teach your model. The wild thing is, all three of these stem from the exact same inability to automatically trust text outputs against source texts.
Which brings us to Section 2, meet NLI, the duct tape holding everything together.
So let's define exactly what NLI is. At its core, natural language inference is simply the three-way classification of a relationship between two pieces of text, a premise and a hypothesis. It really just asks a straightforward question. Given a premise text, is a hypothesis text entailed by it, contradicted by it, or is it just entirely neutral? It's just one single task, right? But it has at least three distinct, absolutely critical production uses. And honestly, this is exactly why every retrieval augmented generation or RAG evaluation framework ships an NLI model under the hood.
Moving on to Section 3, the three labels. We'll look at entailment and beyond.
I absolutely love this classic example. It makes it so clear. Okay, let's say we start with a super simple premise. The cat is on the mat. Label 1 is entailment. If our hypothesis is there is a cat, well, that is definitely entailed by the premise. Any human reading the premise would instantly conclude the hypothesis is true. Label 2 is contradiction. If our hypothesis is there is no cat, the premise completely, 100% rules it out. And label 3 is neutral. If the hypothesis is the cat is hungry, well, there's really no inference either way. The cat might be totally starving, or it might have literally just eaten. The premise simply doesn't tell us, so it's neutral.
And this brilliantly illustrates a really vital distinction. Notice the heavy emphasis on the word natural. You see, NLI is based on what a typical human reader would infer. It is not strict mathematical logic. In strict first-order logic, the sentence, "John walked his dog," doesn't technically mean John has a dog unless you painstakingly axiomatize all the rules of possession. But in natural language inference, a normal human reader implies possession immediately. It's all about modeling human understanding, not rigid math.
All right, Section 4, data and architecture. Let's look under the hood.
The history here is basically a rapidly escalating arms race in machine learning difficulty. It all kicked off in 2015 with SNLI. That had 570,000 human-annotated pairs, which was huge, but it was narrow, mostly just image captions. Then 2017 brought multi-NLI, which expanded things to 10 distinct genres and really became the standard training corpus. But by 2019, models were getting way too good at the easy stuff, so NLI was born. This was adversarial. Humans literally wrote examples specifically designed to break existing models. And then by 2020 and 2021, we moved to Duct NLI. This tested long-range, multi-hop inference across massive entire document-length premises. The evolution here is just staggering.
Now, remember that zero-shot classification problem we mentioned a few minutes ago? Here is exactly how NLI magically solves it without needing a single drop of training data. Step 1. You take your document and your list of candidate labels. Step 2. You verbalize those labels into hypotheses, something like, this text is about sports. Step 3. You feed the document as the premise and the label as the hypothesis into your NLI model, and you compute the entailment probability. And step 4, you just pick the label with the maximum probability. That's it! This incredibly elegant trick is the exact mechanism behind Hugging Face's hugely popular zero-shot classification pipeline. It just works right out of the box.
Next up, Section 5, the 2026 stack. Here are the models you can use today.
Consider this table your ultimate 2026 utility belt. For general-purpose NLI, the open default dominating the leaderboards right now is Microsoft's DeBERTa-3-large. If you need something super lightweight for fast, edge zero-shot classification, BART Large MNLI is incredible. For handling massive, document-level text, you'll definitely want to look at the models trained by Moritz Lauer. And if your primary goal is hallucination detection in RAG systems, tools like Ragus and DeepEval have NLI layers built right into their core. You don't have to build any of this from scratch. The stack is totally ready for you.
Finally, Section 6, pitfalls to avoid. You definitely want to watch out for these. Just let that number sink in for a second. 60%. What does that actually mean? Well, it turns out that on early datasets like SNLI, models could predict the correct label 60% of the time by looking only at the hypothesis. They were entirely skipping the premise. They were just cheating using shortcuts. Words like nobody, never, or not heavily correlate with the contradiction label. So if you aren't super careful, your model isn't actually reading your source document at all. It's literally just playing a statistical guessing game based on negative words in the summary. Building on that scary thought, here are the core pitfalls you absolutely must avoid. Aside from those hypothesis-only shortcuts, there's the lexical overlap failure. Basically, a simple heuristic like, if all words in the hypothesis are in the premise, it's entailed, will completely and totally fail against adversarial datasets like SNLI. Then there's context length. A model trained on single sentences will see its accuracy completely tank, degrading by 20 points or more on document length premises. And finally, domain mismatch. Standard models are trained on general English. If you throw dense legal, medical, or scientific texts at them, they're going to stumble unless you use domain-specific models like SNLI or meta-NLI.
And get this. This pitfall is incredibly surprising. When you are doing zero-shot classification, your prompt template matters immensely. Simply comparing the phrasing, this example is about label, versus just throwing in the label completely bare, or saying the topic is label, can literally swing your model's accuracy by 10 points or more. No joke. You absolutely must tune your verbalized template for your specific use case.
As we wrap up this explainer, I want to anchor everything we've talked about on this one really profound quote from the source material. NLI is the duct tape of text understanding. It is the hidden layer. It's the basic utility. It's the glue that ensures these massive, flashy AI models are actually telling the truth and grounding their outputs in reality.
So, I'm going to leave you with this provocative thought to chew on. The next time you're building a system and you need to mathematically prove, does text A support text B? What are you going to do? Are you going to automatically reach for another slow, massive, and incredibly expensive LLM API call? Or will you be a smarter engineer and reach for the duct tape?